All right, welcome back. So let's talk about our second video. How do we factor numbers? So in other words, how do I factor a very large n? Up to this point in time, if for instance, I'm just going to give you an n that you have factored before, but what if I gave you 100? You know it's not prime, so you know it has to break into some numbers that multiply together. But how do I know what that factors into? Well, we can start checking. We can be like, okay, well, this is even, so I'm going to take a 2, and that's going to give me 50, and then I'm going to have to factor 50. So I can take another 2 out. That's going to give me 25. What number is going to 25? Now, again, if you're telling a computer this, the computer doesn't automatically look at 25. Like you and I can look at 25 and be like, oh, that's 5 times 5. But the computer doesn't know to do that. All it knows how to do is, all right, let me check a list. And it literally would run through this recursive process step by step up to checking values. That kind of guess and check is extremely inefficient. So how do we factor? Well, one of the first ones is called Fermat's difference of square method. And this is actually really, really useful. Let's suppose that n is an odd number bigger than 1. So, and it's a product of two numbers, r and s. Where r, as I said before, we're going to suppose that r is less than the square root of n. So n is not a perfect square. That would just make this horrible. So if that's true, then it can be written as n is equal to a squared minus b squared, where a equals r plus s over 2, and b equals s minus r divided by 2. And the only reason I do, remember, s is the bigger one. That's why we have s minus r, not r minus s over here. Okay. Then in order to factor this, we only need to look at the values of x, where x equals y squared minus n. Why? Why do we have to do this? Well, if you think about that real quickly, I can rewrite this statement right here as n equals y squared minus x. So I'm going to pick some y value that starts at the square root of n, because remember, it has to be bigger than the square root of n plus one more. So I'm going to use the floor function plus 1. If you want to look about this in different, you could have also, this is how it's often written, but you could just written this whole thing right here is also equal to the ceiling function, and then under the ceiling function, the square root of n plus 1, and so forth and so on. Because if I round down and then add 1, same thing if I just round it up. The one catch 22 would be if, well, n happens to be a perfect square, and that's anyways. We go all the way up to n minus 1 divided by 2, and we're just going to look at this list until we find a perfect square. Because essentially what we're doing is we're trying to find an x that is a perfect square. Boom. So you better have a list of perfect squares in order to do this. So this strategy is really, really good. It actually is a very common factorization strategy that is used in a lot of programming, but it takes a little bit of time to understand. So often what we do is we use the floor functions. That way I'm just always using the floor function plus 1. Floor function tends to occur more often than not as well. So this is just going to work our way through all the way up through here. All right, so let's see an example about how this actually would be executed. Let's consider number 1159. Now, 1159, that may sound familiar. That was from our last homework. And you had to factor it, because the only way to do an encryption was we had to break it into its two factors. So the square root of this plus 1 is 35. Not the actual square, but the floor of that square root plus 1 is 35. So I'm going to take that from 36 all the way up to 1,159 minus 1, which is 58, and then divide that by 2, and you get this 579. So I'm going to run through these options. So you notice that means I have over 530 options to run through. That's a lot, but I'm going to go ahead and just build up a table of starting and looking at it. So I got 35, it gave me 66. 36, well, it gave me this number right here, and so forth and so on. And this is the key number right here. So if I build this list, and this is really easy to build an array and execute the things on array in Python. If you want to do Python, you can do a lot of different coding things. And then you essentially are going to check each of these and say which of these is actually its square root is an integer, and work your way through there. But this turns out this is the number right here, 441, which is 21 squared. So that's when A is 40 and B is going to be 21, because that means that 40 squared, because this was my y value squared, minus n was equal to 21 squared. So that means that literally, so you all can see this again, that 40 squared minus 21 squared is equal to 1159. Now, going back to your algebra days, that means that this is equal to 40 minus 21, 40 plus 21. Normally, we would say that this is how we get this, but there's one key thing that we're missing, that is not the R and S we're actually going to get. We actually have to do a little bit of, because we actually did some times 2 in here, and that's what's messing this whole thing up. So what I'm going to do, so if I'm working through this, we have to then solve, again, going backwards, n equals a squared minus b squared, where a equals r plus s, because I could take this and literally do this r plus s, r minus s, but the over 2, this is, you might be like, well, where'd that over 2 come from? That's just because we're actually just dealing with the fact that this is kind of hanging out here. So I get this, and I can factor it, and turns out that's 61 times 19. And again, the way I solved this, I just made this a system of equations. Just all of you. So if I have these two equations right here with two unknowns, it's just a system of equations. So again, that means I'm going to write them above it. 40 equals r plus s over 2, which I can write as 80 equals r plus s. And then similarly, 21 equals s minus r over 2. So 42 equals s minus r. And I just took these two systems of equations, combined them together to get my answer. Now you may also notice that a and b, a plus b is s, and a minus b is r. So both ways we get our answer, we can work this out, and we have thus solved our equations. All right, so hopefully it's making a little bit of sense about how this strategy works. So again, this is factorization is Fermat's difference of square. It will work for all odd natural numbers. But the key problem with it is that you're having to do a whole lot of squares. Squaring things, not hard. But finding all these iterations, which is essentially n over 2, which is still an order of n, yeah. And so for each one of these, I have to square it, square it, square it. This turns out to be an order n problem. It's not really a great way to factor something. So it's really annoying. It's really bad, especially for large numbers. Euler came up with a different way, but it only applies to integers can be written as x squared plus ay squared equals z squared plus aw squared. In other words, I can write it this same a, but different x, y, z, and w. That is the big deal. So this only works for integers that I can write them in this form. And if that's the case, then what I do is, this is where this is really, xw squared is equal to n minus a y squared w squared, which equals negative a y squared w squared, which is equal to z squared minus n y squared, which is congruent to z mod n, I mean, z times y squared mod n, which pretty much means that x times y, so my x times y and my y times z are either equal or negative versions of each other mod n. That's the critical part, mod n. And then the trivial, this only tells us we have a factor, and the factor is given by the greatest common divisor of xy plus or minus yz and n. All right. Wow. That was a mouthful to say. So let's just do, with this one is actually a little bit trickier. It's one reason I'm not going to really do an example. This one, again, it's also hard because it only works if I already know it's in this form. And that's the key part. So let's talk about a different one that actually we can use a lot more for factoring again. So again, we use the first one. We use, for Ma's method, we don't really use Euler's a lot. It's really useful for a lot of different stuff. But one we do use is Pollard's, which we want to factor n, and we choose a smoothness bound of b. Whoa, you just threw a new word at me. It's okay. Smoothness bound pretty much means that all primes that divide it are no larger than b. That's a slight problem. Because how do you know smoothness bound? Well, you just need a prime number that's bigger than the square root, and guarantee that's smoothness bound. Oh, we don't know that for certain. So here's what we do. We choose A, which is going to be our base, and it's going to be somewhere between 2 and n. And then we compute the greatest common divisor of A and n. If that greatest common is bigger than 1, well, we just found a factor of n because we now have number. Otherwise, we go on. So if it's 1, move on to step 2. In step 2, we take all the prime numbers less than or equal to b, and we compute m equals the natural log of n divided by that natural log of prime number, and then round that down and replace it with and replace a becomes a to the p to the m. So wait. So you can kind of see that again. We pick a p value, a prime number that's smaller than b. Then we compute this, which is the natural log of n divided by the natural log of p, round down. Then a, so remember a was our original value we just picked. We're going to swap that out. We're now just going to take that number to the p to the m, where p is, again, my prime I picked, and m is this round down value. By doing that repeated square process, we're just going to square it up and replace it in. But this becomes my new A, essentially. This whole thing will become my new A. So this is for my first prime. So my second prime is going to have a bigger base to work off of, and then my bigger base and so forth. Well, doing this, but all I'm doing is raising to a new power. So it's just multiplying all those powers together. And we eventually get the product of all those powers, their corresponding M. And once we have that, we go to step 3, which is to compute the greatest common divisor of A minus 1. Remember, A is not this, is now that we've gone through this process to get a new A, that's our max A. We're now going to take G, we're going to take the greatest common divisor of that minus 1 and N. And if that's bigger than 1, then we have a factor. Otherwise, the algorithm is, well, unsuccessful and just kind of leaves us hanging there, not knowing what to say. And again, if it fails, it just doesn't tell us anything. If it works, it gives us factorization. Just because it didn't find a factorization doesn't mean there doesn't exist one, it just didn't work out. So we're going to go through this process. So let's kind of look at a number. And again, I'm not picking that massive number I started off for factorization. That's not even fair. Again, I can't write down all those steps and other things. So n is that 44,712. The smoothest bound is 13, and a is 2. Then we want to know, we know that a is relatively prime because it's not odd, so we can just move on. So again, reminder, pick a base. What's its greatest common divisor? In this case, it's 1, so we go step 2. So what we're going to do is we're going to look at all the prime values all the way up to 13. Again, I have to pick the smoothest mound that I'm going to be checking it up to. That is where the problem comes. You have to pick this B. If you pick it wrong, it does not help you. So sometimes we're like, I think there's something, whatever. But here I get 2 times 3 times 5 times and 7, 11, and 13. These are the first 5 prime numbers. So each of these is the natural log. So this, for instance, is, as a quick reminder, I'll come back up here. It's the natural log of my n value divided by the natural log of 2. So notice as my p values get bigger, I'm dividing by larger and larger values. So this is going to get smaller. So this 15, let me write that down. We're going to take the natural log of 44717 and divide that by the natural log of 2. And then we're going to round that down. That is going to be our 15. And you can check my calculations on this and so forth. The second one, I would just replace the 2 with a 3. And then I would replace the 3 with a 5 and so forth and so on. So that is all my P's and my M's. Okay. So step 1, I chose A is 2 and B is 13. I wrote down all the P values. Then I can literally just take a minute, quickly calculate all these M values. It's just a straight calculation. It's really easy to do. Then what I'm going to do for this one is I'm going to take A, which is 2, to P, which is 2, to the 15th power, mod N. Well, 2 to the 15th power really means I'm just going to break this up and just do, it's really nice because it's an easy binary expansion because it's, well, 2 to the 15th power. So I can just take A and I can square it, square it, square it. This one, though, I'm going to take that, let's call this one A hat. Here, I'm going to take A hat and I'm going to raise that to the 3 to the 9th power mod N. And that should give me this thing right here. And then we take this whole thing right here, we replace it, and we raise that to 5 to the 6th power mod N. That's going to give us 3,300, 38,000. And we keep going through this process over and over and over again. All right, so does that hopefully it helps make the iteration process make a little more sense about what we're doing. So again, we do this, and then we need to take the greatest common divisor of A minus 1 and N. But A minus 1, A, as a quick reminder, is this value right here because we're replacing A every single time. So we're doing a calculation, we're putting it back in using A so we can calculate it in the next step. So now we take the greatest common divisor of those things, which is the greatest common divisor of 4,171. And my N, 44,717. That greatest common divisor is 97. Go ahead and run your Euclidean algorithm. Boom, got it. It's 97. Well, that tells me right there that 97 is a factor. So now I can just take how many times 97 go in 44,716. Turns out it's 461. 47 is smooth since p minus 1 is 25 times 3, which that's really nice. And but Q is not, since that's equal to 22 times 5 times 23. All right. So hopefully that makes a little more sense and you're feeling like you're getting the hang of all of this. And we're kind of working our way through these different numbers. Let me know what questions you have, and I'll help you out more. Good luck.